We look good. We're live.
Alive. Hello everyone. My name is Zavar. I am one of the co-leads of the Hybrid Engine team. For those of you who came last time, I was not there. I was feeling pretty sick, so Andrew gladly took over for me. But yeah, back here today. So for today, we first have Avi talking about the combustion chamber. Then we have Andrew, known as Lark, talking about the injector. Then Avi again with the igniter. And finally, Ashish twice for fuel grain and the thermal protection system. Cool. So now I'll leave it to Avi to talk about the combustion chamber.
All right. So I'm Avi. I spoke last week on testing, but I'm back talking about the combustion chamber. And let's just get right into it. The combustion chamber is the section of the engine where the fuel and oxidizer actually meet and react. It's essentially just a pressure vessel that's meant to contain the combustion reaction and direct the byproducts of combustion into the nozzle. For our engine, we're just using a stock cylindrical aluminum tube with machined end caps that interface with the feed system on one side and a nozzle and retainer ring on the other. In between the end cap and nozzle, we have to implement some kind of thermal protection to keep the aluminum from weakening due to the heat of combustion. For our purposes, we determined that a layer of canvas phenolic composite material would provide adequate protection, and Ashish will talk about that a little bit more later on. Okay, so functionally, we divide the combustion chamber into 4 distinct regions. We have the pre-combustion chamber, the fuel grain, the post-combustion chamber, and the nozzle. The fuel grain will be talked about a little bit later today, and then on our next session, we'll talk about the nozzle. But the pre-combustion chamber is essentially just a volume of uninhabited space in between the top end cap and the fuel grain, where hot oxidizer flow recirculates and combusts along the leading edge of the fuel grain to increase combustion efficiency. The pre-combustion chamber is also where the igniter sits, which is just a little pyrotechnic donut that sits right on top of the fuel grain and kicks off the actual combustion reaction by just inserting a high amount of energy into the propellant mixture. And then the fuel grain is just a cylindrical block of solid fuel that reacts and combusts with the flowing oxidizer. Now, most of the fuel and oxidizer will be combusted in this region, but some of the unreacted chunks of fuel get entrained in the oxidizer flow and they get carried farther down into the chamber, where we call it the post-combustion chamber. This is, again, just another volume of uninhabited space where the unreacted propellant collects to increase the likelihood that all the propellant will react in the engine. And when the fuel and oxidizer react, they produce a mass of hot gaseous byproducts that are then expelled through the nozzle to generate thrust. So there's a good deal of testing involved in verifying our combustion chamber. Hydrostatic testing will ensure that the seals in the chamber are tight and that the chamber can hold the high pressure. Hot firing will test that the TPS is effective in shielding the walls from heat and that the combustion byproduct can be contained before being expelled through the nozzle. There's a good amount of work left to complete for the combustion chamber. We have to do some calculations and analyses to verify that our TPS will be able to contain the heat of combustion. We also need to do some redesign and remachining of our end caps and the chamber. And then we have to manufacture some fuel grains and igniters. Those are some fun tasks. It's just like cooking or baking with a group of friends.
Ooh, fancy last name on this one. Okay, so we're going to start talking about injector design, which is fun because we got a lot of questions about this last week. So, okay, so the injector is this piece that's circled on the right in green, and it's located at the top of the combustion chamber. So it has 2 main purposes, and one is to deliver the liquid oxidizer from the upstream oxidizer tank and feed system into the combustion chamber at a dependable rate. The second main purpose is to atomize, which means to turn the liquid into very fine small droplets and distribute those atomized droplets along the surface of the fuel grain. Combustion happens along the surface area, so the maximum interaction with the fuel grain surface area creates the optimal combustion. Because the injector is what's actually delivering the oxidizer onto the fuel grain, they're extremely important to determining your engine performance. And it's also the last piece of hardware that your oxidizer is touching before it starts to combust. So the injector is commonly considered part of the feed system because it's what's feeding into the combustion chamber, but it's also the point where the feed system and combustion chamber meet. And the combustion chamber is made up of a lot of pieces that we have designed and machined ourselves, while the feed system has a lot of commercial components that we've bought off the shelf. So we commonly categorize it along with the combustion chamber parts, but it's really kind of more of an intersection. Okay, so our design, which you can see our actual pictures of here on the left, is what's called the shower head injector design. So it's called the shower head because, well, it looks like a shower head. It's like, it actually just is the same design as what's on your shower. It has these vertical holes, or perpendicular, however you want to call them. And in this case, they're called orifices. And this is chosen mostly for the simplicity of design, and it's easy to manufacture. So our design features 37 orifices with 1.16 millimeter diameters and a height or length of 8.12 millimeters. On the right, I threw in a picture of a bunch of different other types of injector designs. So this is taken from a source that's talking about liquid engines, liquid bipropellant engines, which have the liquid oxidizer, but also a liquid fuel in their case. So you can see those separated between the green and red. But so you can see how they're all different types, especially when in liquid engines, there's an extra purpose that they need to worry about, which is the mixing of the two propellants. Since they control the flow of both types of propellants, they control how they mix. So you have all different types of injector designs here. So there are a couple that have been used on famous engines. So this one here is the concentric tube with the liquid swirl, sometimes called a coax. That was used in the space shuttle main engine, the RS-25. A series of like doublets right here were what was used in the Saturn V's F1 engines. And in this case, the green oxidizers will meet and hit each other. It's called impingement, where they are angled right at each other. And when they hit, that's how they atomize and become small droplets. And then since they're both being atomized near each other, that's how they mix. And then this pintle injector here is being used right now on the SpaceX Merlin engine and also on the Apollo lunar lander. So like we said before, the shower head is something we use because it's very simple. It's easy to design. It's easy to design in the way that you can also predict what's going to happen without a lot of complex fluid dynamics. There is still complex fluid dynamics, but it's a bit simpler here. So yeah, that's how we've gotten started with this project. So as I mentioned, those orifices are a bit easier to design. So here's a little bit of an intro into how we designed it. So if you were to look at this diagram on the bottom right, which is a diagram of what we would consider one orifice, essentially you determine the size of one orifice and divide that as if you were designing one orifice for the entire injector, and then you divide that by the number of orifices that you choose based on the actual sizing of the total injector. But you would do that based on a couple of variables that you know and assumptions. So you would know like the up and downstream pressures. So up and downstream is a term that's used a lot in fluid dynamics stuff, and especially in a rocket engine. And that just basically talks about like the direction of the flow. So the flow of the oxidizer goes always from the oxidizer tank, which is upstream or at the top, down to the combustion chamber, which is downstream. So your upstream pressure is what would be in the feed system, and your downstream pressure is your chamber pressure. And the difference between the two is what's known as the pressure drop. So as the oxidizer enters the injector, you need to induce the correct pressure drop to ensure that the pressures remain what you want it to be up and downstream. You also have to have a given oxidizer mass flow rate. So this is one of the vocab words from the other day, but it's defined in kilograms per second. So it's the amount of mass that flows through a specific area every second. So this number is actually determined from how you deal with the thrust in your fuel grain, to get the proper combustion to get the amount of thrust that we want. So that would be a number that you would do offhand and would be given to you based on your system requirements. And then there are three assumptions that we make. One is that we assume that the flow is in single phase, and what this means is that the flow or the liquid oxidizer will remain a liquid throughout. Based on the different pressures and temperatures, there are certain circumstances where the liquid will evaporate into a gas, and then you have two-phase flow, which is incredibly complicated. And even today, it remains an area that's a big area of research, and it's one of those kind of fluid areas that aren't super well known. So avoiding that ended up being important just because we couldn't predict what would happen during two-phase flow. A second thing we assumed is incompressible flow. So incompressible means that the flow is moving at a speed where the density of your liquid doesn't change. And as you might guess, this is important because if the density of your liquid is changing, that also really complicates the equations that you're using and how you calculate everything. So I think all the aero classes, there are two fluid classes, AE through 11, AE through 12. One is incompressible flow and one is compressible flow. So you'll get to learn about both. And it's important to learn both because you'll have compressible flow in other areas of this engine, like the nozzle, for example. And the third thing is that you assume steady state performance. So this means that you would calculate and design this for when the engine and the injector are operating at its peak performance. So essentially when the engine starts, it might take a little bit to kind of build up as the flow is just starting. So you don't need to worry. We're not worrying about that in our calculations for this design. So this equation here is derived from Bernoulli's conservation of energy equation, and also the equation for a constant mass flow rate. I can show you more about this later, but right now it's kind of just algebra. You combine those two equations together and you get one nice equation at the end. And based on this diagram, where A1 is essentially like the diameter of your feed system when it's entering your injector, and then A2 is the size of your individual orifice, you'd want to solve for this variable A2. So you know m dot, which is your mass flow rate. So anything with a dot on top is commonly a derivative with respect to time. So you'll see that a lot in all of your classes and stuff like that. You also have rho, which is density, delta P, which is your pressure drop, which we mentioned before. And you have one other term here, which is CD, which is the discharge coefficient. So this takes care of any losses that might be happening and a loss is essentially like a loss of energy or something that might slow your flow down. So as it's moving through the orifice, the length of the orifice, there's going to be some frictional losses. There's also going to be a loss as it's entering the orifice because it might hit the side as it moves in. So stuff like that. So that kind of just normalizes it and accounts for anything that might be happening. So there's a way that we theoretically check for atomization. And atomization, again, actually if you look at the graph here, there's a really nice image in the upper right that shows the atomization regime. And you can see how it's exemplified by these really, really fine and small droplets. And as I mentioned before, the surface area interaction between the oxidizer and the fuel is what you're worried about for combustion. Yeah, so Raj just answered the question in the chat about CD, the discharge coefficient. So I'm actually just about to mention that on my next slide about how we verify that. So the more droplets you have, each droplet, even though they're very small, the total surface area will be much higher. So it'll create even greater combustion. So we're looking to have a very strong atomization regime. And you can verify that through two non-dimensional numbers. Non-dimensional numbers are very common, especially in research and in the use of research in the fluid dynamics, when you're comparing the characteristics of maybe two different fluids at different conditions. It's a way to show their flow conditions based on their what they're moving at, so at their speeds and their mass flow rates and stuff like that. So two numbers that are used to verify here are the Reynolds number, which is one of the most or more common non-dimensional numbers that you'll see. They want to get bogged down to the equations, but conceptually it's a ratio of the inertial forces to the viscous forces. And the other one is the Ohm's storage number, which is a ratio of the viscous forces to the square root of the inertial forces, inertia and the surface tension. Yeah, so my next slide should be on testing. So we can verify it through theoretically, we can verify that our injector will work through design and also through that graph I just showed for the atomization. But for anything that we're working with, you can't really verify it until you test it, which is why testing is such a big part of the process of getting to a launch, and also this year specifically. So there's one test that we do called the cold flow test, where most of the test is really aimed at testing the injector and also the feed system, but just because those are so important to the performance of the engine. So on the right here, we have the P&ID, which is a piping and instrumentation diagram, and that just shows the components that would be in your system. So you can see that in this test, we don't need the combustion chamber because we're not trying to combine the oxidizer with the fuel. We're not trying to combust anything or ignite anything. So we actually remove the combustion chamber because we also want to visually see how the flow is being distributed. So like right here on the left is a picture of just a generic cold flow test that's being done with water, and you can see how it's being atomized and distributed, and they even have a tape measure in the back so they can visually measure it. But the two main things we're looking at are to determine that the mass flow rate that's occurring is the same that the mass flow rate that you've designed it for, and you also want to determine your injector discharge coefficient. I forgot to mention that when you initially calculate the equation for the mass flow rate to determine the orifice area, you actually make an assumption that you start with an initial discharge coefficient of 0.7. So this has been commonly found just through lots of empirical or experiments. And the idea is that you start with that, and then as you test, you'll be able to actually determine that value and see how close it is, and if you need to do any further design from there, then you might need to, but that's how you take care of that until you get to test and actually find it out for your own injector. So as there was a question in the chat, rocket science, there is a lot of plumbing. And here are igniters.
Hey, Avi, are you here?
Yeah, I'm on.
Okay.
You want to get the next slide? Yeah, sorry. Okay. So for most fuel and oxidizer combinations, you actually need to introduce a significant amount of energy into the system to actually initiate the combustion reaction. And based on the type of engine and fuel that you're using, you have various ignition methods at your disposal. Higher tech igniters are a very simple form of ignition. They're kind of like fireworks. It's just a simple compound that you just put high voltage across, and that'll produce a high amount of heat and light, and that has minimal byproducts. You also have electrical ignition, which is where you just have exposed bridge wires where you, again, just have a high voltage across them, but they'll actually spark and induce the reaction in the propellant mixture. And then the last class of ignition is chemical or hypergolic ignition. It's usually used for liquid engines, and that's where the fuel and oxidizer will actually spontaneously combust when they come into contact with each other. And for these ignitions, you actually need to time them very accurately to initiate the combustion process properly. If the igniter doesn't ignite on time, what can happen is a hard start. That's where the local pressure in the combustion chamber is too high, and the ignition occurs in a high pressure environment, and that's basically a bomb, and we don't want to be making bombs. So to prevent a hard start, we're going to have to do a good amount of testing for the ignition system to figure out what the latency in triggering the ignition and the actual ignition is, to coordinate that sequence with the initiation of oxidizer flow into the engine. And for our engine, we're using a rocket candy-based pyrotechnic device, and I'll talk about that a little bit more in the next slide. So rocket candy is just a mixture of sugar and potassium nitrate that is used pretty widely in amateur rocketry as just a simple solid propellant. It's pretty easy to work with because it can be mixed and formed into shapes without any huge risk of spontaneous ignition. And you can sort of tinker with the actual mixture and composition to get a more desired reaction. And for our purposes, what we want is a short, high energy, high temperature burn. So to actually get that exact reaction, we're gonna have to do a good deal of testing and documenting different burns to figure out what our best recipe is. It should be a pretty fun project. We just get to cook up a bunch of different mixtures, ignite them, and see what the best design is.
Okay, Ashish, before you start doing your cool fuel grain stuff, can we stop for questions? Because I forgot to stop for questions after my section.
Sure, I have no issues.
And unless there are no questions, then we're just way too good at their jobs.
Seems like
We do need stamp remover. That is something that's not easily available.
Yeah, we'd love to have some. When we first started making this, we had to. One of our members drove around to like every hardware store and like department store in the area looking for it. It was impossible to find. Then she's just had a bottle of it for some reason.
Yeah, I drove 50 minutes to get some
I
remover.
had a bottle.
Yeah,
of
it's hard to find.
Yeah.
experimenting
But yeah,
about
we'd
it.
appreciate any extra you have, Michael. Thank you.
Yeah, sure.
All right, any other questions? Okay, Ashish, take it away.
All right, can you guys hear me clearly?
yeah, sound good to me.
Good.
Okay. All right. So hybrid rocket engines basically store the oxidizer as a liquid and the fuel as a solid, which creates a configuration that is mechanically simple and also reduces the chances of like an unwanted chemical explosion, either in flight or like during ground operations. So upon ignition, a flame develops over the fuel surface, which causes the solid fuel to evaporate, thereby sustaining the combustion. As the fuel comes in contact with the oxidizer, being fed through the injector through which it is atomized, as Andrew mentioned earlier, combustion occurs in a boundary layer diffusion flame adjacent to the surface of the solid fuel grain, hence producing the exhaust flow gases which generate the required thrust after expansion through the nozzle. A boundary layer is basically a very closed region next to a surface over which a fluid is flowing, where the effects of viscosity are non-negligible. You will learn a lot more about it once you take A311, which is in compressible flows, and a lot of aerodynamics have to do with like studying boundary layer, turbulent or laminar flows. So that's another thing in itself. It's a huge whole thing. But yeah, anyway, so different fuel grain geometries affect the ISP variably. So like for instance, as you can see on the right over here, if you have a circular fuel grain port geometry, then the thrust curves look something like this. And the ISP is basically the integral of the thrust curve with respect to time. So like the area under this curve changes. Next slide. Okay, so once we know the total impulse required, we can calculate the oxidizer and fuel mass based on chosen propellant combination. That's where the CA analysis helps a lot because it kind of gives us the data that we need to make decisions on different types of geometries that we can choose or mass of propellant, etc. So the geometry of the grain is again decided on the basis of the thrust curve or like the kind of flight mission that we want to have and like how easy it is to manufacture. The most simplest one is again the circular port one because it's easy to manufacture and also it has a very simple regression rate model as given here. Regression rate is basically the burn rate or the rate at which the fuel is burning away after coming in contact with the oxidizer. So for paraffin and nitrous oxide, we can choose, there has been like a lot of studies done in the past, like on this combination of propellants. So we can use a simple regression rate model, which is A Gox of N, which is, all of these are empirically determined after experimentation. So for paraffin and nitrous combination of propellants, there are multiple sources which cite different values for these constants, but they're within the same range. And once we know the regression rate, and again, using the like expected rocket performance parameters, so like for example, you know what your mass flow rate is, which is of the propellant is basically the force upon the ISP G naught. So the force is basically the amount of force you're expecting to gain to reach the kind of altitude that you're planning for. So in our case, we're planning to reach 10,000 feet. And for that, we will require a 4 kilonewton total force. So these are just calculations based on that. And then once you have these figures, you can use that to determine the dimensions of the fuel grain using the 3 equations given below. So in our case, we only need to know the diameter of the grain, the diameter of the port within the fuel grain, and the length of the grain, which are all correlated to each other. Next slide. Okay. So once we know all the theory and we have all the data, we start manufacturing the grains. We first determine the fuel grain composition, which the CEA helps with. So for our engine, we're going to be having 60% paraffin wax and 40% aluminum grain when we launch finally in IREC. But for now, we're going to have a pure paraffin wax grain manufacturing agenda because we first want to test it out. And also, there's a lot of work that still needs to be done into figuring out how to manufacture homogeneous mixture of grains with aluminum and other additives involved. So after calculating the dimensions of the grain based on the equations that we just saw, for paraffin, we came up with 2 processes of manufacturing fuel grains. One was just heating up the wax to its melting point, which is around greater than 60 degrees Celsius, and then pouring that hot wax into the canvas phenolic tube directly, which is the thermal protection system that I will talk about more later. And then the other process is you use a spin casting machine, which is basically something that ISS developed before even I was here as a freshman, in which they use a lathe and they connect use a PVC and like end caps and then connect it to a tube in which they spin hot paraffin wax at a very high speed, which causes a homogeneous mixture. So on the right, at the bottom of the screen, you can see the fuel grain that I made over the summer using a 3D printed matrix inside it. And then on the left, you can see the fuel grains that were made by using spin casting. And you can see that it's so much better using spin casting. Okay. Thermal protection system, yep. So the thermal protection system is basically between the fuel grain and the combustion chamber's inner walls and protects the structural integrity of the chamber from high temperatures reached during combustion. A method of safeguarding the chamber walls is to use the material inside, such as canvas phenolic, that can provide insulation and protect from the heat of combustion, and also have a low enough thermal conductivity to decrease the likelihood of expansion of the chamber walls. So as more heat is applied to aluminum or any specific metals, they usually tend to expand. So we want to limit that because otherwise that can cause catastrophic failure in terms of the structure of the chamber itself. Aluminum 6061 T6, which is what we're going to be using, commonly has like a specific yield strength for temperatures ranging in 25 to 100 degrees Celsius. And it is the ideal construction material for the chamber because of its lightweight, and it's also the most common used material in aerospace applications. So the yield strength of the material remains relatively constant between a temperature range of 25 to 100 degrees Celsius. Therefore, the objective of the TPS is here to keep the temperature of the aluminum during in-flight below 100 degrees Celsius. So in order to compensate for that, we use canvas phenolic as the ablative material because it's a poor conductor of heat. It also holds very similar properties to glass epoxy material, which has an ablation rate of 0.02 millimeters per second, which is a very good ablation rate for an insulating material. And this has been analyzed before by a paper or a study conducted at KTH, which is an engineering school in Sweden. So it is safe to assume that the material can withstand a conductive heat transfer, and therefore we have different levels of thickness at different regions of the combustion chamber. So the light blue region you see is the pre and post combustion chamber, which will have an insulation layer of 0.5 inches thick, because that's where the ignition is going to be happening towards the injector. And then towards the nozzle, that's where all the hot gases and propellant mix will accumulate before going through expansion through the nozzle. So we're focusing more material over there to limit the conductive heat transfer. And then surrounding the fuel grain, we'll have a 0.25-inch thick canvas phenolic tube, because the temperature will be very high, but not as high as a pre and post combustion chamber. And also the fuel grain will be burning itself. So, okay. So I'll switch on my video now and I'll try to show you guys the demonstration.
I thought you were joking about that. Didn't know you actually had a demo.
No, Andrew said that we can do it the last time we talked about it. Yeah, here's the fuel grain that I made over the summer. Pure paraffin. Here's the blowtorch. So the blowtorch is basically an igniter, and assume like, so if you look at it this way, this is your injector right here. I don't know if you can see it. And it's gonna atomize the oxidizer in a way that it goes like this.
Be careful here, Sheesh.
Watch your hands, buddy.
So
yeah, a good question, Michael. Is there, in case things go bad, you got an extinguisher in there?
this is like the boundary layer diffusion that I was talking
No
about.
need.
So you can see the wax melting inside of it. That's it.
Sick.
Sick. So yeah, that was all we had for today. Didn't have an immediate slide, which we normally do. But yeah, do you guys have any questions about anything we talked about today, or anything involving rocketry in general?
Can you go back? There was like a slide or two ago that had like a picture of the engine on it. Yeah, that one there. Is that like generally what we're planning on the engine looking like? Or is
Yeah,
that combustion chamber?
more or less, yeah. The only difference is that the end caps that are gonna be changed. So like the lilac color aluminum that you see there on the ends of the combustion chamber tube may or may not look the same, but everything else, yes, will look similar.
Okay, cool. And then do you I forget, I think we've mentioned it before. Do we know the diameter of the rocket yet?
Yeah, we do.
Yeah. So the fuel grain diameter, the grain diameter, like the outside grain diameter, is 3.45 inches. And when you add the TPS on top of that, you add like 0.25 inches more. So I think the inner diameter of the combustion chamber is 3.74 inches. So that should add up to it.
That was Gabe that asked that, right?
Yeah, I was asking for the
rocket body.
Yeah, the rocket body, and then for just because I'm looking up stuff for like the engine retention stuff, so I was just trying to get a little bit more information on it.
Yeah, I'm forgetting the number for the rocket body. I think Angel is here, I believe.
6 inches, right?
Yeah, I thought it was
right, 6 inches, and then the booster tube for the hybrid engine is 5 feet, 5 feet long.
5 feet, 6 inches.
6 inches. Okay.
Mm-hmm.
Big shout out to Angel, Ira Ked.
Thank you, Andrew.
I'm going to go ahead and send a link to our wiki, which has all the details about calculating fuel grain dimensions.
Yeah, so a lot of this, Nick asked if there's a place that has all this information. The majority of our information is on our wiki. And then she's just posted a link to that.
Awesome.
There's actually a technical overview page, which has a lot of figures and numbers on it, which is very useful for anyone working on any other teams who just like wants to look up some stuff.
Are there any other questions about TPS or fuel grain?
Or life.
Yeah. Me and Andrew, we have a lot of wisdom when it comes to life. It's mostly Andrew. I feel like you're generally a pretty wise figure.
I don't know about that, but that sounds really cool. I'm gonna start telling people that.
Let's play the harmonica or something.
I do. You want me to play? Is that?
Well, no, I'm just saying, generally in my mind, people who play the harmonica have like a jaded, like wise experience of them, you know?
I don't know if jaded is the right word.
No, yeah, maybe not jaded.
Not but yeah, I can see that. I can see that.
Yeah.
I can play something. Though.
Yeah, I mean, if you guys don't have any questions right now, at least me and Andrew would probably be here until 9 o'clock. If anyone thinks of something and like wants to chat about rockets and stuff. But we don't necessarily have anything else to present about. So if you guys want to head out, you're free to go. Or if you want to stick around and chat with us and hear Andrew play the harmonica, more than welcome.
We said Andrew's gonna play the harmonica.
Thing was that a lot of fuel grain stuff is going to be hands-on this semester. So if you're like interested in working on that, you can either message me on Slack, Discord, or whatever.
Yeah, so good thing to note, the fuel grain stuff and the igniter stuff are very, very hands-on. The igniter is just a lot of like literally testing rocket candy and like making it burn and explode.
I guess for just like structure sub-team stuff, do we know how thick the aluminum flanges are going to be? Yeah,
Don't quite yet, but we're gonna know very soon.
Okay, sick.
So I think you're referring to the end caps, right? The flanges for the end caps.
Yeah, for the end caps.
Yeah, those are still being designed right now.
Okay.
But those are like the first thing to finish up in our design. So.
Okay, sick.
Yeah, did someone have a question about rocket candy when I mentioned it? I don't know if someone was said something.
Oh, I was just saying that that's a great term. It should be used more often.
Is that? I actually don't know.
That is just like the term for it, because it's just sugar and then stump remover. So
yeah. So that's the official term.
Though.
That's just not what we say, right?
Yeah.
Okay.
I mean, there's no official, because it's not like any sort of like technical or official thing. It's just a widely accepted term for that type of explosive, I guess. Pyrotechnic.
Pyrotechnic. Wow. Good word choice.
That's good.
Boomy stuff. Okay. Saturday. Yeah, so our next and final session of Crash Course is going to be at Saturday at 5:30 p.m. So make sure to stick around for that. Josh asked a very good question. Are we not getting any harmonica, Andrew?
Oh, I can get some. I wanted to make sure all the questions were done. I didn't want to just start playing and people were trying to figure out how rockets work and stuff.
Okay, actually, yeah, maybe that's a good point. I don't know. People have any more questions?
I had one quick question. Do you guys have an idea for how long altogether the hybrid engine plans on being? Just ballpark.
So I think we have a ballpark right now, and I forget it off the top of my head. We have very firm or pretty good numbers. Well, we have a very strong number for the combustion chamber and the oxidizer tank, and then we need to measure the feed system because that has a lot of like commercial parts that we need to like kind of fit together like a jigsaw puzzle.
So as Andrew just said, the combustion chamber and the oxidizer tank we're pretty sure about, but the feed system actually is variable right now, and something that we need to discuss with IREX structures about how long we want it to be. Because besides the length of all the commercial parts, there's tubing in the middle that we're just taking a long tube and cutting down the size for each section. So if we want, we can make that pretty short in certain areas or make it pretty long if we need to.
Okay. Yeah, it was just something structures was considering, and they were looking into like how to like splice fiberglass tubes, and then there's also manufacturers that have like custom quotes if you need longer than like the 5-foot commercial tube. So just something that I didn't know if they wanted to look into, if that was something that would be needed, but that works.
Yeah, I think one of the first things we're planning on doing with the feed system is figuring out the length of it, because we were under the assumption that IREX structures would want to know at least a ballpark estimate of how long the entire engine should be.
That's good.
Yeah, and as it stands, I think we only have 6 inches of leeway for the feed system that goes in between the combustion chamber and the oxidizer tank. Because the combustion chamber is like 2 feet long, and the oxidizer tank is 2.5.
We have 6 inches of leeway?
Because it's 5 feet total, right?
For one segment, right?
Yeah. The combustion chamber is 2 feet, and the oxidizer tank is 2.5 feet. So we have half a foot leeway as it stands right now.
From just like me thinking about what's in the feed system, I don't know if we could get that all in 6 inches.
I would say, and in the booster tube, it houses.
Yeah, 6 inches
the-
seems to be pretty short.
Yeah.
Yeah, it's
when I
along
added
with
it,
the-
we had more like a feet or so.
Yeah.
Like 30 centimeters for the feed system. And since we switched since we switched components, it's actually probably going to be longer. So yeah, 6 inches seems pretty short.
Angel, what were you saying?
Oh, just that also there's, within the booster tube, we have the parachutes with the shock cord and U-bolt that'll also be taking up, X amount of space. So longer tubing, something to look into. Got it.
Yeah.
I can, like the check valve is about this long. The main ball valve is also about this long. And the solenoid valve is a little bit longer. So, including all the connecting pieces between that's going to probably be over a foot. I was thinking maybe like 2 feet.
Okay. Yeah, that's all right. Cool. Noted.
So custom link quotes, let's go.
Are you really planning on making the feed system longer than a foot?
It's not something that we were planning on doing. I just feel like that's how it's going to end up being, given the number, like the components that we have in it.
We have 3 parts that need to be placed one after the other, right?
Yeah.
Which is check valve,
Main ball valve,
and main ball valve. The
Actually,
solenoid valve isn't placed in line.
Well, no, there's also the T-splits that also are considered like an element.
There's 1 T-split.
2. Isn't there one for the pressure transducer? For each pressure transducer, each PT has a T-split, and the solenoid valve has a T-split.
You are correct.
So
Yeah.
there's also the T-joints, which I think there are 3, and then 3 elements. For those of you who weren't on hybrid, this is all going to be a lot. But basically, we're just trying to count the number of components that are actually in the feed system because their lengths can't be changed. So if we add up all of their lengths, which is something that we should do pretty soon, we can get like the absolute minimum length of the feed system. And the actual length is going to have to be longer than that because there has to be piping in the middle to connect all those.
Got it. I can't wait to build a 20-foot tall rocket at this point, just so that we can fit everything in.
We almost did it last time. Guess we'll do it this time.
Is there anything bad with that?
The two biggest things is the structural integrity. We don't want it to like in the middle that puts a lot of strain and can rip it in half. And then secondly, we can't be taller than the launch rail. Is like our limitation. It's like a safety hazard, I think, so.
Yeah, I mean, that makes sense. And we're not increasing the diameter, are we?
No.
Yeah.
I looked up how long the check valve is, and it is 4 1/8 of an inch long.
Yeah.
That is long.
Yeah, like that thing is like this long. Well, just so you know, we talked about this when we were talking about tasks for hybrid, but whoever's doing feed system with me, that's like one of the first things we're going to do is just figure out lengths.
Yeah.
And like, actually, I described it as dimensioning. So like figuring out how much diameter space we're going to need and actually how long the feed system's going to be.
I can get some harmonica in while we think. All right, this is Pano Man, not Piano Man. Ooh, I fucked that up. Fuck. I missed a note there. I feel real bad about that.
Actually,
was that too loud also?
No, it wasn't.
Beautiful.
It was
I was
great.
scared that would be too loud.
I was going to address what Jack asked about what we're doing after Saturday. And this isn't hard set out yet. We still have to talk about what the plan is, but it's probably going to be all of us meeting together and anyone who's interested after all 4 days of it, of CCP, who really wants to join the team. And we'll give a short presentation about what we actually have left to do and how we're going to sort of divide our teams up. As of now, the plan for our team is to, for each component that we've discussed, assign one returning member and 1 or 2 new members and have them sort of work together in a small group on it. And we're not really sure how we're going to divvy up everyone and all that, but there'll be a meeting where we just kind of at least talk about what is left to do, and we'll work from there. Oh, you have a SoundCloud?
I have 2 albums on there. I have like several views.
I forget that you have an album.
I tried to put it on Spotify, but I realized that all my songs are covers, which is like a big like copyright thing. I'd have to like start paying a lot. It's unfortunate.
I very much appreciate the Andrew Larkey experience.
Yeah, that's probably my favorite. I think Alarkinator Summer got more commercial claim, but I think I sold out a bit.
It's funny to think that the official recording of this is going to have your harmonica in it. Thanks for coming, Luke. Have a nice day. I was going to say something, but I'm forgetting now. Oh.
I'm going to get out of here too. Thank you guys. This was awesome.
See you later, dude.
Nick. What else?
Thanks, guys.
I'm gonna head out as well.
Bye.
Adios, dudes.
See you later.
Thanks, guys. I'm gonna head it.
Yeah, I'm gonna end the recording now then.